Welcome to Pre-Calculus. Today we will investigate writing inverses of exponential functions. We'll take a look at two examples. Our first example is the simple exponential function y equals 6 to the power of x. So our goal is to, first of all, write the inverse equation for this exponential function, and then I want to create a table of coordinate points for this original and the inverse, and then from the table sketch my graphs along with the identity line. Let's tackle that first task first, which is to write the inverse. So when I've got a exponential function like this, to write the inverse is really as simple as switching my domain and my range, which in an equation are represented by the x for domain, y for range. So to make the inverse, initially all I have to do is switch the x and the y. So my inverse is going to be x equals 6 to the power of y. And as with all inverses, that is the true inverse. But for it to be graphable, I need to solve it for y. So if I were to put some steps, if my first step was to switch x and y, my second step is going to be solve for y. Now, with other inverse pairs, we've got some algebraic strategies that we can do to solve for y. For exponential functions, we really need a conversion rule because the inverse of an exponential is going to be a logarithm. So the conversion rule that we would use, and it's right at this point since this is a simple exponential function, if I've got base b to the power of a equals y. Let me make that a different variable just so that we can see it. We'll call that c. The way that I would convert this to a logarithm is by saying logarithm base b. So you always start with the base of whatever's on the opposite side of the equal sign. So log base b of c equals the exponent a. And so I can use that rule to convert from the exponential form to the logarithmic form. Let's go ahead and do that here. So for this equation, again, I've got it a little bit flipped around from here. So my base in this case is the 6. So I would start my conversion as log base 6 of, we'll go the opposite direction, but it's really to the other side of the equal sign of x equals the exponent y. And if I invert that, I have my inverse function y equals log base 6 of x. And that is my inverse equation. So I'll go ahead and box that. Our second step is to graph these. So let me make a table for both the original and the inverse. So here's for 6 to the power of x. And we'll choose for our domain -2 through +2. And these we can calculate by hand. They're pretty straightforward. If I put in a -2 power, that's going to be 1 over 36. So almost 0. 6 to the power of -1 would be 1 over 6. 6 to the power of 0 is 1. Anything to the power of 0 is 1. 6 to the power of 1 is 6, and then 6 squared, 36. Now, when I go to sketch the inverse table, I'll put it right next to the table of the original. So I'll go ahead and put x, and this is log base 6 of x. I could go ahead and use the same domain. In fact, let's go ahead and do that. So I want to actually make a change because there's a kind of a essential relationship between an inverse and its original, to where if I took the original table, I really don't have to recalculate for my inverse. I just need to switch the x column and the y column. And it's the same idea as switching x and y variables at the beginning for the equation. So I'm going to just use what I got here. So my x values are going to be my old y values. So 1/36, 1/6, 1/6, 36. And then my y column would be my old x column. So -2, -1, 0, 1, and 2. So let's graph from what we've got here in our tables. We'll keep it color coded so that we got our two functions distinguished from each other. So here's the exponential. -2 is almost at 0, 1/36. -1's pretty close to that, 1/6. And then typical of exponentials, it hits the y-axis at 1. 1 is 6, and then I can't really graph 2/36. That's off my screen. So I'll sketch in this exponential function. And there's my y equals 6 to the power of x. Remember, an exponential function is going to have a horizontal asymptote. So I'll sketch that in on the x-axis. Well, let's sketch in our inverse. So 1/36 -2 is almost on the y-axis for the inverse, the log base 6 of x. 1/6 -1 is still almost right on the y-axis. And then very typical of log functions, it's going to hit the x-axis at 1. And then at 6, it's got the value of 1. And again, 36, 2, it's way to the right, so I can't graph it. So let's place our log base 6 curve. And another feature of inverse functions is if the original had a horizontal asymptote, because of the switching of domain and range, the inverse will have a vertical asymptote. So I'll sketch that in. And that's complete. The last thing I want to do is just place the identity line, which will reveal some stuff about my inverse writing. So identity goes through the origin, then has a slope of 1/1. So it just rises from corner to corner. And we're looking for two things on the identity. If the original intersects the inverse, they should do so on the identity. These are not intersecting, so I don't have that feature, but I do see a reflection of the original across the identity line to the inverse. If I were to fold that purple one over the green line, it would land exactly on the blue line. And that completes that first example. Let's take a look at a second example that involves a little more manipulation algebraically. So we'll jump down here to number 7. So again, our task is the same. I want to start off by writing the inverse equation, create tables, and then graph. So again, I've got my function here. To write the inverse, I just have to switch x and y. So I'll start x instead of y equals, now everything else is in place, so parentheses, fraction, e to the power, what will change is this variable, y, instead of x, plus 6 over 3 to the power of 1/5. Now, solving for y in this case involves more steps, quite a few in fact. So I need to get it down to a form to where I have this e to the y isolated. Once I've got that isolated, I can make the conversion over to a logarithm. So I'm just keeping my eye on e to the power of y. What I need to move is the 3, the 6, and the power of 1/5. So let's start with the power of 1/5 since it's the thing on the outside. And to get rid of that power, I just need to raise everything to the power of 5. And that's going to cancel that power of 1/5. I will also raise the x to a power of 5. So on the left, I've got x to the 5th equals now, without parentheses, the fraction e to the power of y plus 6 over 3. So again, just with my eyes on e to the y, I now need to move the 3 and the 6. So the thing to move now is going to be the 3. by multiplying both sides by 3. So now on the left, I've got 3x to the 5th. There's no longer a fraction on the right, it's e to the y plus 6. And again, just to track what we're trying to isolate, e to the power of y plus 6 only needs subtraction by 6 to get e to the y by itself. So that'll cancel on the right. On the left, we get 3x to the 5th minus 6th equals e to the power of y. So at this point, we are ready to make our conversion. So I'll put it in the order that's presented to us here. So I would have used b to the power of a equals c. So that's kind of the same structure we've got. So just to identify parts, my c is this 3x to the 5th minus 6. What do you think b is? That's the base e, and then my a is y. So the conversion would be base b, log base b of c. So log base b of c equals the power a. So let's make that conversion here for ourselves. So log, our base is going to be this e. So log base e of, in parentheses, 3x to the 5th minus 6 equals that old power of y. And all of a sudden, we've got our inverse. Y equals log base e of 3x to the 5th minus 6. I will make one conversion here. Since I've got log base e, a more conventional way to write that is as natural log ln. So I'll make that conversion 3x to the 5th minus 6. And that's the one I'm going to box. The one that includes the anytime I see log base e, really a way to write that is ln, natural log. Okay, so we've got our equations. What's up to us now is to make our tables. So let's create our side-by-side tables here. Again, the only one we need to really calculate is the original. So I'll put x, -2 through 2, and then more here, e to the x plus 6 over 3 to the power of 1/5. So since there's a lot more to write there, what I want to do is take this over to the graphing calculator online and get a table there. So I'm going to record it and bump over to Desmos. And let's type it in. So our function is y equals parentheses, and then I've got a fraction e to the power of x, plus 6 over 3, all to the power of 1/5. And there's my exponential curve. So you can see the asymptotes lifted up so that it's really kind of above 1, it looks like. Let's get a table. So I got my -2 through 2. And so it's a very flat graph. Let's write it down though. So at -2, the output's 1.15, 1.16, 1.18, 1.24, and 1.35. Just given that this is a very flat curve, I am going to include some other values here. So at 3, we've got 1.54. We'll keep going. At 4, we've got 1.82. 5 is going to be 2.20. 6 is going to be 2.67. And let's go ahead to 7 because I want to get some values so that when I graph my logarithm, it's got some points to plot. So that looks like it'll work for us. Let's head back and graph our function. Back to the notes. So I'll just fill in the table with what we just calculated. So I'm going to just zoom down here and include up to 7, 3, 4, 5, 6, 7. So then our outputs were 1.15. It didn't climb much at all in the negatives. 1.16, 0 is 1.18, 1's 1.24, 1.35, 3 is 1.54. So it starts to rise as it heads to the right for sure, not a lot. 5 is 2.20, 6 is 2.67, and 7 had passed the 3 marker, 3.26. All right, so that lets us graph. So we'll just plot these points, -2, 1.15, -1, 1.16, 0 is 1.18. Very slow rise to begin with. 1 is 1.24, so about a quarter above 1. 2 is 1.35, getting closer to half. 3 is 1.54. 4 is 1.82, so getting close to 2. 5 is 2.20, so it passes the 2 mark. 6, 2.67, and then 7's 3.26, just a gnat's whisker above a quarter. So here's our exponential original function. Very, very slow growth, but it does show growth. And I've got a horizontal asymptote. It's not exactly at 1. It's a little bit higher than 1. I don't know exactly what it is, but I'm going to pencil it in just so I can see it there. Well, we're ready to graph our inverse. That'll complete this task. So we can do the same thing we did before by putting x and our inverse, which is natural log of 3x to the 5th minus 6th. And I could calculate that on Desmos, or I could switch my table. Let's switch it. So I'm going to make my old y column my new x column. So 1.15 is -2. 1.16 is -1. So notice I'm just switching the values. The old y's become my new x's. Old x's become my new y's. And again, that's because these are an inverse set. They can demonstrate this quality of switching the domain and the range. So 1.82 is 4. Make sure I write that correctly. 2.20 is 5. 2.67 is 6. And 3.26 is 7. So where I had to really estimate my y values on the original, I need to estimate my x values here on the inverse. So at 1.15, I'm at -2. So just a little bit past 1. At 1.16, I'm at -1. At 1.18, I'm at 0. At 1.24, I'm at 1, so about a quarter past 1 there. At 1.35, I'm at 2. At 1.54, I'm at 3. At 1.82, I'm at 4. 2.20, I'm at 5. At 2.67, I'm at 6. And then lastly, at 3.26, I'm at 7. And I can sketch in my logarithmic inverse now. So it's going to arise from -infinity, cross over the x-axis, it'll continue to grow over to the right as the x values increase. Again, since I had a horizontal asymptote on my original, my inverse is going to have a vertical asymptote. So we'll sketch that one in. Again, it's a little past x equals 1. And then to finalize here, we just need to place our identity line. So this pair of inverses do intersect here on the identity line. And in fact, there would be a second intersection if I let these two endpoints keep going. They would also intersect on the identity. My sketch here wouldn't show that because it's a little estimated as I went past 7 there. But it does show that intersection here closer to the origin. It also shows the symmetry. If I were to fold the original purple over the green line, it would land exactly on the blue line. Thank you for joining for this investigation of writing and graphing inverses of exponential functions. See you soon.